Hi everyone, my name is Dion Rossiter. I'm the Executive Director of Science at Cal at UC Berkeley. Welcome to our very first Midday Science Cafe, clearing the air, empowering communities to improve air quality. So I have an exciting lineup for today, but first let me just go ahead and introduce what Science at Cal is. Science at Cal supports the advancement of the public's understanding of science and technology and engineering by creating opportunities for the UC STEM research community to share the wonder and the excitement and the relevance of their research with the public, which includes you. We are all online now, as is the rest of the world. So this is our first, as I said, Midday Science Cafe. I will go ahead and hand the screen over to my colleague at Lawrence Berkeley National Lab, Jennifer Tang, and she will go ahead and introduce the program. But we will first have Alexis Shusterman, who's a lecturer in the College of Chemistry at UC Berkeley, presenting. We'll go ahead and ask Alexis a few questions. Then we'll go ahead and give the floor to Dr. Chelsea Preble. We will then ask further questions. So please enter your questions into the chat. As Dr. Shusterman and Dr. Preble are speaking, you can ask as many questions as you like, and we'll go ahead and give each one of them a chance to answer questions at the end of their talks. Then we'll bring everyone together and we will go ahead and ask a bunch of questions, all the questions we didn't get to after the end of their talk, so we can come together and have a conversation with both of them. So again, I'm going to hand the mic over to Jennifer Tang at Berkeley Lab.
Thanks, Dee. I appreciate it. Do you mind flipping the screen? And actually, we should land on the Science at Cal page just so folks get a chance to see that first as well. As Dee mentioned, my name is Jen Tang, and I'm the manager for Federal and Community Relations at Berkeley Lab. For those who don't know, Berkeley Lab is one of 17 U.S. Department of Energy national research laboratories across the country. We're supported by DOE's Office of Science and managed by the University of California. Since its founding nearly 90 years ago by a UC Berkeley physics professor named Ernest Lawrence, Berkeley Lab has been dedicated to advancing the scope of human knowledge and seeking science solutions to some of the greatest problems facing mankind. Today, Berkeley Lab researchers develop sustainable energy and environmental solutions, create useful new materials, advance the frontiers of computing, and probe the mysteries of life, matter, and the universe. All of our research is unclassified. As part of the UC family, Berkeley Lab enjoys a highly productive relationship with all of the UC campuses. Approximately 200 UC faculty have a joint appointment at the lab, and we're also home to several hundred UC postdocs, grad students, and undergraduates doing research at the lab. As you can imagine, Berkeley Lab's relationship with UC Berkeley is especially close, and our institutions have joined forces to advance science on many frontiers. One of the main motivations for creating this new Midday Science Cafe series is to share with you examples of compelling and complementary research from both of our institutions. We hope you enjoy today's presentation and look forward to highlighting other science stories in the future. Back to you, Dee. Thanks.
So I'm going to go ahead and hand my screen over to our first speaker. Thank you, thank you. So Dr. Alexis Shusterman completed her PhD in atmospheric chemistry at the University of California, Berkeley. How exciting! While working with Professor Ronald Cohen. Her graduate work centered around the construction of Beacon, a high-density network of more than 36 low-cost sensors capable of providing community-level air quality reports throughout the San Francisco Bay Area. During graduate school, Alexis worked with science communication and outreach organizations nationwide to spread climate change and environmental justice awareness, winning recognition in the UC Berkeley Grad Slam, the University of California Carbon Slam, and the American Chemical Society Champions competitions. Now a lecturer in the UC Berkeley College of Chemistry, Alexis, Dr. S. for her students, now dedicates herself to delivering high quality chemical education full time. So go ahead, Alexis.
Thank you, Dee, for that lovely introduction, and I'm really excited to be here with you all today. I just wanted to get started with an image that maybe some of you have seen before, or maybe you've seen similar images, if not this particular one. This set of images shows us the city of Milan, Italy, both before and after they began sheltering in place related to the COVID-19 pandemic. In case you couldn't already guess, this image here on the left is our before shot that shows us this really hazy horizon as well as some limited visibility that is of course corresponding to air pollution. Species like ozone, which protects us when it's up high in the stratosphere but is bad for us down here in the troposphere where we live. Carbon monoxide, NOx, which refers to a family of nitrogen oxides where the X can stand for a 1 or a 2, as well as PM or particulate matter. So the main thing that changed between the image here on the left and the image on the right that led to this huge reduction in air pollution is that folks stopped driving their cars. There are lots of different sources of air pollution. Cars are not the only source of pollutants, but they are the source that we as individuals have the most control over, and they're what I'm going to focus on today. So the main chemistry that happens inside of your car is combustion. Combustion takes all of the different components of gasoline. It's a pretty complicated mixture, but here I am showing you an 8-carbon compound known as octane, and it reacts with oxygen in the air to produce carbon dioxide and water. And if combustion was all that happened inside our cars, we wouldn't worry about air pollution at all. We would worry about global climate change because carbon dioxide and water are both greenhouse gases, but neither of them are directly harmful to human health in the concentrations they're present in the atmosphere. But unfortunately, combustion is not the only chemistry that happens in our cars. We also have to worry about incomplete combustion, where instead of adding 2 oxygen atoms to each carbon, we can end up with just 1 sometimes. That makes toxic carbon monoxide. And sometimes not all of the carbons in octane fully break apart. And so we end up with this sort of carbonaceous clump that's known as particulate matter. That specific form of particulate matter is known as black carbon or soot, and that's what Chelsea is going to talk about in just a few minutes. The inside, the engine of our cars can also get so hot that side reactions can occur that have nothing to do with combustion at all, including the oxidation of just nitrogen, N2, the most abundant gas in our atmosphere. At the temperatures inside your car, it can be oxidized to NO, which then goes on to do subsequent chemistry and make ozone. So all of these pollutants are potentially produced by the chemistry of our cars. And we as atmospheric scientists are really interested in measuring these air pollutants. But this measurement is really a needle in the haystack type of problem. These pollutants are measured in units of parts per million or parts per billion even. And so that means we're sifting through millions or billions of other gas molecules in the air looking for the species that we actually want to measure. Thankfully, always up for the challenge, atmospheric scientists have come up with some solutions to this problem. The instrumentation for atmospheric measurements kind of falls into 2 main categories. One being light scattering and attenuation techniques, where you have some kind of light source, such as a light bulb or a laser, and some light detector. And as pollutants flow or float in between the light source and the detector, they can either scatter the light away from the detector or absorb the light, which dims the amount of light that gets to the detector. So from measuring the light at the detector, we can infer what the concentration of pollution in between must have been. Another technique that is often used is electrical current generation, where you have some kind of circuit with a little voltmeter or maybe an amp meter, and then atmospheric species stick to one of the electrodes. And depending on how many pollutants are stuck to the electrode, that might either produce or reduce the amount of current flowing through the circuit. And from there, you can infer the pollution level as well. If these techniques sound a little complicated or a little bit fiddly, that's because they are. They can be tricky to get right. And so these instruments that perform these techniques in a high precision and high accuracy fashion also tend to be very expensive. And if you've ever bought anything expensive, you know you don't tend to buy a lot of it, right? You just buy as few as you can get away with. And so this high cost of instrumentation leads to some pretty sparse air quality monitoring networks. What you're seeing here is my hand-drawn outline of the Bay Area. So here we have the San Francisco Peninsula, we've got Marin County, Berkeley with Oakland down here. And each one of these blue dots is an air quality monitor maintained by an organization called the Bay Area Air Quality Management District. And at each of these blue dots, they have a whole suite of these very high precision, high accuracy instruments that are also high cost. And so that's why there's only 12 of these dots on this map that are attempting to represent the air pollution experienced by the entire Bay Area. But what atmospheric chemists like myself know is there's actually a fair amount of spatial variability in pollution levels that isn't captured by a network like this. So for example, really close to a roadway where the cars are actually driving, you see really high concentrations of air pollution. I'm representing that here with this hot red color. But due to just clean air blowing through and some chemical reactions, even just short distances away from the roadway, you can see significantly cleaner air. And so we end up with this sort of distribution of air pollution around roadways that has these high spikes right near the road and then lower background levels further from the road. This might not seem like a very big deal, but if you're one of the people who live really close to the roadway, that means you're experiencing a much higher level of air pollution relative to folks living further away. And so this has implications for where we then place our air quality monitors. An air quality instrument that measures this neighborhood farther from the roadway is not necessarily capturing the air pollution burden that is placed upon the near roadway neighborhoods. And so this is really a science issue and a measurement issue, but it becomes an equity issue when we remember that these further from roadway neighborhoods are often more expensive to live in. And so what we have here is a systematic subjecting of lower socioeconomic status neighborhoods to higher burdens of air pollution. And it's not just that it's cheaper to live near a roadway, it's that we also tend to build roadways in lower income neighborhoods in the first place. This is done by a process known as eminent domain, which, if you aren't familiar with it, is the power of a government to take private property for public use. Public uses such as roadway construction. That's how we constructed the BART here in the Bay Area, as well as post offices, other public uses like that. The definition of public use has gotten rather flexible over the years and has also included turning over these private properties to private developers as well. And eminent domain in and of itself isn't necessarily a bad thing, but it turns out that property seized via eminent domain tends to be disproportionately property found in neighborhoods that house racial and ethnic minorities, that have low median annual income, and have residents living below the poverty line. And so the issues of racial and economic justice that have really been at the forefront in our national conversation over the last weeks to months are also really issues of public health. The World Health Organization estimates that each year poor air quality leads to 7 million premature deaths worldwide. And for those who are able to live with poor air quality, there are ramifications as well. Respiratory distress, including increased asthma incidence, cardiac distress, such as heart attacks and strokes, as well as even reduced cognitive functioning. There have been studies that show students who take standardized tests under poor air quality conditions don't perform as well on those standardized tests. And this all becomes even more worrisome when we consider the fact that air pollution is just one of many intersecting issues and risk factors that are often concentrated in the same neighborhoods and populations. So neighborhoods affected by air pollution tend to also experience limited access to healthcare, as well as limited access to outdoor space for exercise and recreation, as well as political disempowerment. So issues of voter suppression often mean that the folks most burdened by these other risk factors are least able to advocate for the rights and regulations that would protect them. So this really brings us to the idea of environmental justice, which the US EPA defines as the concept that everyone, no matter the color of their skin or their income or their religion or their sexuality, is entitled to the same degree of protection from environmental and health hazards, as well as equal access to the decision-making process to have a healthy environment in which to live, learn, and work. So environmental justice is really the driving motivation behind the air quality monitoring efforts that I have been a part of, as well as the specific air quality monitoring network we're going to hear about from Chelsea in just a few minutes. So I'm excited to hear her presentation as well.
Alexis, thanks so much for that really compelling presentation. Before we move on to Chelsea's presentation, I've got a couple questions for you from our audience. The first is there a general range for how far away from highways one must be to avoid the most significant public health threats?
That's a great question. And of course, being a scientist, my answer has to be, it depends. So it does depend on the traffic load on a particular highway, because that's going to dictate what the peak of the pollution is that you're experiencing. And then the decay away from that will be affected accordingly. But it's generally viewed to be on the order of hundreds of meters. So once you're a full kilometer away from a roadway, you're probably experiencing background levels of air pollution. Whether those background levels are healthy levels or not depends on where you are. But between 0 to 1,000 meters is generally seen to be the range of the most impact of the roadway.
Thanks. One more question for you. How does weather like rain, wind, heat, or cold impact air quality and air pollution? For example, when it's cold, exhaust from cars seems more visible. Does that mean that there are more pollutants in the air?
Ooh, great question. This is a really complicated intersection of variables, but the main issue is going to be circulation. So if you have conditions that are leading to the air to blow through more quickly, then you're going to have lower concentrations of air pollution. Whether that happens because of warm air or cold air depends on the topography of the area that you're in and the dominant wind directions. So if you're in the Bay Area, you might recall a few falls ago, we had some really significant particulate matter pollution from the wildfires in the east. And we were experiencing a really unique wind pattern during that time. Normally air blows west to east in the Bay Area. But the kind of perfect storm of weather conditions in that moment brought the air from the east into the San Francisco Bay Basin. And because there's just that little tiny Golden Gate opening, the air really got trapped there. So wind is a big issue. Rain can be kind of a cleanser for the atmosphere as well. A lot of these species that we worry about are soluble in the water droplets of the air and will fall out of the air when it rains. Not something we've gotten to experience very much in the Bay Area recently, but that can be a really big lifesaver if you're experiencing poor air quality and you finally get some of it to rain out.
Wonderful. Thanks, Alexis. So it is now my pleasure to introduce Dr. Chelsea Preble. Chelsea is a UC Berkeley postdoctoral researcher, and she's also an affiliate at Berkeley Lab. And she is proud to be a Golden Bear through and through, having earned her bachelor's, master's, and PhD from UC Berkeley. In her work, She seeks to better understand air pollution trends that affect people and evaluate the real-world emissions impacts of new regulations and alternative energy technologies. Her research includes characterizing in-use emissions from heavy-duty diesel trucks and commercial hovercraft, quantifying emissions from organic waste diversion systems, and developing community-based air quality sensor networks. Over to you, Chelsea.
Hello, everyone. I'm very happy to be here today. I'm going to first just apologize if you hear any loud banging. There is some work going on at my house, just one of the challenges of working at home in this time, but hopefully that doesn't bother us. So I'm really excited to spend the next 10, 15-ish minutes to talk about the community scale air quality monitoring work that we did in West Oakland here in the San Francisco Bay Area. And thank you, Alexis, for that fantastic overview of air pollution and why it matters to understand it at a more block by block level. That provides a lot of really important context for what I'm about to talk about. So to understand what the community that we were looking at, West Oakland is a community that's burdened by diesel exhaust. And so like Alexis was saying, black carbon is a really important constituent of diesel particulate matter that's emitted at the tailpipes of trucks, boats, other diesel sources around an urban environment like this. And that's of concern because diesel exhaust is carcinogenic and toxic. So if you live in an area where there are a lot of these sources, there's some real health implications associated with long-term exposure. And so one such community is West Oakland. It's surrounded on all sides by major freeways, as you can see in this map. It's adjacent to the Port of Oakland, which is the 5th busiest port in the US, as well as the associated rail yards. And so there's trucks that often travel through and around this community on their way to these major freight handling facilities. And that's on these designated truck routes, which are shown here as the blue roadways. There's also prohibited truck routes within this community that are shown in red as an effort to protect the community from exposure to this diesel truck exhaust. But there's a caveat with that rule in that if you're a business on that roadway that requires trucks to access you, then trucks are allowed. So it's, I would say, loosely enforced as opposed to strictly enforced. There's also many truck-related businesses that are scattered throughout this community that are still bringing in trucks. And so those are shown as the gray rectangles. So because we know of this large sources in this area, the Air District runs one of their monitoring stations in this community. So one of those blue dots on the map that Alexis showed is in this community, and it's denoted by the star on this map. And this site includes measurements of black carbon, which again is the major constituent of diesel particulate matter. When you think of a truck, you probably think of that big black sooty cloud that comes out of the tailpipe. And so what we wanted to understand is, given the number of diesel sources in this community, how do ambient concentrations of black carbon vary in space and time as a function of these sources? And so what we did for a period of 100 days is we took ambient monitoring in this community from that single starred location to 100 locations throughout the community. And so we call this the 100 by 100 study for 100 monitors for 100 days. And what we did is we created a dense network of custom-built low-cost black carbon sensors. And that's because, like Alexis said, the commercially available instruments that are really high accuracy and high precision are just too expensive to buy more than one of them. So what we did is we created something that we call the aerosol black carbon detector, or the ABCD. And for us, that has a unit cost of about $500, which is much more affordable than the commercially available instruments that are more like $20,000. A lot of this cost reduction is because we weren't a business, so we didn't have, the O&M costs associated with the business. And instead, we relied on a large group of undergraduate and graduate students to build and deploy and maintain these sensors. So thank you to the many dedicated students that this work wouldn't have been possible without that team. And what we did is we put these sensors in these waterproof nodes. I actually have one of them right here. So it's small. It's smaller than the size of a shoebox. It's waterproof. And inside it has all of the pieces that make the instrument run. So that includes a battery, a pump to pull air through it, and some brains, so a little mini computer to log the data. And what we did is we just zip tied them to any available surface that we could around the community. So that included on fences and on porches and poles. And what was really great is that we actually asked the community members themselves to act as hosts for our sensors. And so we placed them outside of homes and businesses throughout this community. But this work wouldn't have been possible without some really meaningful partnerships that we fostered over several years of working together. So on the research side from UC Berkeley and Berkeley Lab, we had, again, a large team of graduate and undergraduate students that provided the sensors and the technical expertise for this network. But on the community side, we worked with the West Oakland Environmental Indicators Project, and they gave us the community expertise of you know, the knowledge and context for where we should deploy these sensors and how we should interpret the data that we were receiving from the sensors. They also served as the primary communicators between us as the researchers and the community, the neighborhood themselves. And then we worked with many other people. So there were funding partners that provided the funding for the study, as well as funding for providing stipends for the hosts of our sensors, as well as other research colleagues in the Air District and the port partners that provided access to sampling sites. So it definitely was a large group of people that were working together and collaborating to make this work possible. But our main collaborators that just were really key to the success of this project were the West Oakland Environmental Indicators Project. And so this is a local environmental justice advocacy group. They seek to inform neighborhood advocacy priorities, as well as foster political education and make the research and data available and interpretable to their community. And so co-directors Ms. Margaret Gordon and Brian Beveridge, as you can see here in these pictures, have been leading these efforts, and they have a history of implementing community-based participatory research projects to better characterize and document the air quality problems in West Oakland. And so they do this through a collaborative problem-solving model that welcomes anyone and everyone to participate. They've been really vocal advocates for their community. And so we were really honored to be able to work with them and contribute to that process and that effort. Again, working with the community itself was vital to the success of the study. So starting a year before our deployment of the network, we began to work with the West Oakland Environmental Indicators Project to better understand the community itself and to determine where we should put our sensors out. And so the West Oakland Environmental Indicators Project led efforts to recruit those community member hosts, and then our project funders, the Environmental Defense Fund, provided stipends for those hosts, so we were able to offer $150 in gift cards over the course of the network for anyone who was a host for our sensor. And so again, West Oakland community members allowed us to put our sensors outside of their homes and businesses, as you can see in these pictures of a few of our locations. And we really worked to create a well-distributed network that captured the many land use types that are across this community. So that includes in residential and industrial zones, as well as along the designated truck routes that are throughout the community, and then along the outer boundary of the Port of Oakland itself. And so this is an example of some of the results that we got from this network. And so this is a map that shows the 100 monitoring sites in this community of West Oakland. And the color of the dot represents the average midnight hour concentration as we measured it across the 100 days. And so the bluer colored dots are lower concentrations and the red dots are higher, more elevated concentrations. And what we found were some surprising results that really needed some local context to understand. And so the circled points here are those sensor locations that are along the outer boundary of the Port of Oakland. And we were somewhat surprised to find these elevated concentrations in the middle of the night when the port is closed. And so we talked with Ms. Margaret and Brian at the West Oakland Environmental Indicators Project, and they said, well, the trucks commonly line up overnight so that they're first in line when the terminals open up at 5 a.m. So even though these trucks are all supposed to be certified as clean idle, which means that they're very low polluting, we measured significantly higher concentrations in the majority of the West Oakland community where those trucks were located. Similarly, this was a location at a popular park where during the days there were kids camps, soccer camps, and there's a persistent hotspot at this location throughout the day, but we were surprised to see it continue overnight. And so we again talked to Ms. Margaret and Brian, and they told us that there's a trucking facility right across the street from this park, and that they run their truck refrigeration units overnight, and that this was actually an issue that neighbors in the local area had been complaining about because it actually led to some noise pollution that would keep them up overnight. So without this local knowledge, we wouldn't have been able to put these somewhat surprising results into context and really understand what was happening. So now overall, this is kind of a general picture of the trends that we were able to find in terms of how black carbon concentrations vary across this community. So what more in-depth information can we get from a dense sensor network like this compared to what we understand from that single monitor that's always there? And so these colors now show the ratio of the overall average across all 100 days from each location relative to the overall average at that central starred location. And so anything that's less than 1 means that that location has a lower levels of black carbon on average than what's found at that central monitor. And anything that's orange and red means that you have a ratio that's greater than 1, so that those are the more elevated concentrations relative to the central monitor. And what's really interesting here is that within the community itself, we found that around 3/4 of those locations exceeded the central monitor by up to 75%. And so in particular, in the lower bottoms neighborhood, in the southwest corner of the community, in that bottom left corner, concentrations tend to be high. And that's, where they're near truck routes, they're downwind of the freeway, and they're also tend to be more dense in terms of population. There's also many low-income housing developments that are planned for this area of the neighborhood. So there's some considerations here of what can you do in terms of mitigating people's exposure to these more elevated areas. And then interesting, there's also, areas with many yellow dots. So the upper right-hand corner of the neighborhoods tend to have, some lower concentrations than the central monitor on average. Overall, though, partnerships were the key to the success of this study, especially that with the community itself. And this has enabled us to create science to action. So this collaboration built the densest network of black carbon sensors in a single city to date, which enabled us to characterize the variability of a really important marker for diesel exhaust across a heavily impacted neighborhood. Our data set is publicly available and is actually being used by others to validate advanced air quality models. And then on the flip side, the resulting data set is supporting the community's advocacy efforts. And so our data has been informing the community's air plan strategy, which they call Owning Our Air. And that's part of California's new legislation, or Assembly Bill 617, which requires emissions reductions in communities that are most impacted by air pollution. This isn't the only example, though, of low-cost sensor networks to understand community scale pollution. So these AB 617 monitoring efforts are ongoing, and we'll be deploying our BC sensors as part of these existing networks in the Richmond and Modesto areas later this year. UC Berkeley also has a network of sensors that they call Beacon, and these are rooftop monitors that are tracking atmospheric gases and show a much more dense network than what we would get from regulatory monitoring alone. There's also something really cool that you probably have heard about. It's called the Purple Air Network. This is where you can buy a commercially available low-cost PM sensor. I think it's about $200. It's pretty plug and play. So you can put it anywhere you want in your house or outside of your house or business. And then you can join this publicly available and growing network of low-cost PM monitors that's across the world. So, and there's many other examples, but if you're interested in this is something that the Purple Air Network is really really cool that you can participate and better understand the air quality in your own environment. And so with that, I will open up questions to keep the discussion going.
Thank you so much, Chelsea. That was wonderful. We have some great questions to answer, to get answers, excuse me. So I will go ahead and just read one of the comments from somebody in the audience. They said that, I love this example of how important local knowledge is for identifying problems and designing solutions. And I think that that's really one of the highlights of what you all are doing and how you're using this great project to impact communities. So another question we had was, are there any effective strategies that could be used to actually mitigate the poor air qualities at a level of a city block or even at a building level, for instance?
Yeah, so let me just restate it to make sure I understand it. So is there anything we can do to reduce our air pollution on a block by block level?
Yes, if we now know that it exists from these projects, can we do anything? Mm-hmm.
Yeah, so I think it really depends, again, kind of like Alexis said, it depends. In the case of West Oakland, where we could really pinpoint that a lot of the elevated pollution was due to truck activity, some of the really simple things that you could do then are reroute the trucks away from where people live. So make them go the long way around West Oakland, where there aren't people you know, in these mixed use commercial industrial zones, and instead take the pollution away from where people are living and working. So that's one easy example of what you could do to reduce your pollution.
Great. A second question that just came in is, I've looked at purpleair.com in the past, typically on Spare the Air days. The worst level in the Bay Area were always east of the hills in places like Livermore. Is that a different kind of air pollution than in West Oakland?
Yeah, so that's a really good question. A lot of that, I think, has to do with meteorology, where a lot of the wind typically in the Bay Area is going from west to east. And so a lot of the pollution that might be happening in an area like San Francisco or West Oakland or the East Bay is then getting pushed further eastward, where then it can accumulate and have higher pollution levels overall. And so that's where the Bay Area Air Quality Management District's network of monitoring sites is really helpful to be able to kind of track that movement of pollution. And that's how they're then able to call those Spare the Air days of where will we have elevated concentrations that might impact people's health. And then we can stop things like burning to prevent that pollution from accumulating.
Great. And I'll just ask you one last question before we open it up and ask Alexis to join back in. And that's because this question is specific to the sensors. How did you determine that 100 sensors was the right number to deploy in West Oakland? Would you have gotten different results if you had gone with 50 versus 200, et cetera?
Yeah, that's another great question. So I'm gonna be honest, we said 100 by 100 just because it kind of sounded cool. Just kidding. We actually purposely tried to oversample. So we didn't think that we needed 100 sensors, nor did we think we would need 100 days, but we wanted to better understand where there might be kind of a tipping point, and so that we could then design future networks to have something that's maybe a little bit easier to maintain in the long term. And so what we found that, especially in terms of time, you can get the trends for pollution from an area within about 20 to 30 days. And then for the number of sensors that you need, I think it really just depends on the area and the pollutant. So for black carbon, we found that concentrations can actually vary on very short distances, so within 100 meters. So we actually probably would have found more variability if we had more sensors out there, but then that just becomes a little bit wild in terms of how many monitors that you have out there. So there's some other options that you can do, something called mobile monitoring, where you actually put instruments in a car, like a Google Street View car, and then drive that car around and measure the pollution from the street. all over a neighborhood. And so we're kind of trying to merge these approaches to see if we can come up with a hybrid approach to really understand these block by block variations in pollution. So
Great. I'm going to go ahead and open it up, like I said, and allow Alexis to come on back. I also wanted to let everyone know that we have a lot of great questions coming through. So if we want to keep going, surpass 1, we have our panelists until 1:30. So keep those questions rolling in as long as you have them.
Great, thanks, Dee. So we've got some great questions, as she was saying. I think this question might actually be for both of you. And the question is, can these monitors be placed on moving vehicles, such as maybe a bicycle, and be used to analyze the safety of someone's commute?
Yeah, so that's very similar to the mobile monitoring that I was just mentioning. So there's actually something that the Bay Area Air Quality Management District is doing where they've hired a company called Aclima to do this mobile mapping on every street in the Bay Area over the next couple of years, so that we can really understand what these kind of pollution maps might look like on a block by block level. And one of the things you could potentially do with that information is have kind of a Google Maps route specific, where instead of looking for the most efficient time or distance from getting to point A to point B, you could probably try to see what is the best way to have the lowest air pollution exposure. So you might have to go a slightly longer way to work, but your commute would be much healthier for you.
Yeah, I'll speak to that as well. I think one of the challenges with mobile monitoring in a vehicle that is not a car is power supply. So as I mentioned, the kind of 2 categories of measurement techniques, both assume a pretty stable power supply, right? If your light source is varying in intensity, that's going to cause issues in your measurement. If your electrical current is varying, that's going to cause issues in your measurement. And so with a car, there's a car battery, there's the engine that can kind of keep the instruments on board up and running, but it does become challenging to make really high quality measurements if you're just on a bicycle and you don't want to carry a car battery with you on your bicycle. So there are still ways to do that. There are personal air quality monitors that are considered wearable. Their measurements are just not quite as high accuracy and precision.
Agreed. And similarly, motion vibrations can be very tricky for a lot of these technologies. So if you're bumping around on your bike, you'll probably have a lot of extra noise in your data that you're collecting, as opposed to that really high accuracy, high precision that we typically look for when we're doing our research.
Thanks both. So this is another question about the sensors. Can you watch results in real time from any given sensor in person to see what might be causing pollution in a given area?
Again, that depends. So for the air district's data, I think it's all publicly available in semi-real time, maybe not exactly, but they'll give you hourly average values either right away or within a day or 2, I think, of them collecting. It's posted on their website. For the data that we collected for this 100 by 100 study, we did have an online database where we could monitor each individual sensor, which was really key to keeping the network up and running, so that if there's a problem, we could go and fix it right away. For things like Purple Air, and I think even Beacon, those are publicly available maps that are showing semi-real-time data as well. So it really just depends on what sensors you're talking about and which network you're talking about.
Excellent. And I will ask the next question, which has to do with the tricky correlation versus causation. So what can you establish about poor health indicators that is caused by air pollution rather than what is correlated with it? So I'll start with Alexis, maybe?
Sure, yeah. I really appreciate that question. It's something we always have to be on the lookout for as scientists. The tricky part about public health related outcomes is it's pretty unethical to expose folks to an experimental condition on purpose, right? So if we wanted to keep all the variables the same and subject some people to high air pollution and some people to low air pollution, that would not be a good thing for our society to be endorsing. So instead, and I will come in with the full disclosure that I am not a public health researcher, but my understanding is they approach these problems through statistical analyses. So they have a large enough population in their data set that they can control for variables after the fact. So what they'll do is they'll find a subset of the individuals who were monitored or tested, and they'll say, okay, I can find through just the natural conditions of these individuals' lives, these folks had different levels of air pollution, but all have roughly the same socioeconomic status, for example. And so they can kind of tease out the variation. It's not a causal study, that's correct, but at least statistically they can control for those variables. But part of the value of the work that Chelsea is doing is providing spatially resolved data for that type of variable control, so that that can then be fed into these types of statistical analyses in a more resolved way.
Yeah, and then in terms of our understanding of the health impacts, I think in terms of PM, so particulate matter, that's more established than some of the other air pollutants that could be emitted along with or exist at the same time as PM. And so that's why you'll hear a lot of these numbers like the 7 million number is related to deaths associated with PM exposure, because that's what we understand the most.
Great. And will the future work in Richmond and Central Valley locations include both black carbon monitors and purple air PM monitors? It would be interesting to see how the two types of monitors correlate. Do you have any? Yeah, go ahead.
Yeah, no, that's spot on and exactly what we're going to do. And so we're maybe not exactly a purple air monitor, but something similar, so a low-cost PM sensor, because if we can understand the BC to PM ratio, so basically how much of the particulate matter that exists in an area is in the form of black carbon as opposed to other forms of particulate matter, we can really understand the sources better. So, an area that has high BC to PM ratio is much more diesel, whereas something that's a lower BC to PM ratio is going to be something more like maybe wood smoke or just other atmospheric secondary formation of particulate matter. And so when we can understand the sources, then we can try to tackle how do we reduce those emissions so that we can reduce the pollution levels and then reduce exposures.
Great, thanks so much, Chelsea. We've actually got another question for you. Understandably, the data from West Oakland is unique to that location, but are there ways for other communities impacted by poor air quality to leverage what's been learned in the West Oakland Community Air Quality Study?
I think so, especially if what they are impacted by is by traffic and especially truck-related air pollution. So what we've learned is that pollution is very dynamic, and it can vary on the order of an hour or less than 100 meters. And so distances away from pollution are your key way to protect yourself. So if we can make sure that pollution sources are occurring away from people, then that'll solve a lot of the problem right there. You might have heard the adage, the solution to pollution is dilution, and that's somewhat at play here, right? And that very similar to what Alexis talked about, where if you move away from a roadway, the concentrations really drop off quite rapidly within the matter of a couple hundred meters. And so if we're able to get away from the pollution sources, then people will be healthier. So I think we can take those types of lessons learned and push them forward in terms of where do you site new houses and new developments related to roadways and other sources like that.
I'd love to jump in on this particular question as well, because I think it can feel a little overwhelming to think your only option as an individual is to just run away, to get further away. And if you don't have that option, you think, well, what can I do? Something that not a lot of folks know is that our regulations for truck emissions and engine efficiency apply to a fleet-wide average. And so a trucking company makes a whole bunch of trucks, and as long as the average truck meets these standards, it's considered legal. But it's actually very common for what they call drayage trucks, which do these short trips back and forth from, say, the Port of Oakland to a little railway that aren't driving very far. It's very common for a trucking company to use their oldest, most broken down trucks to do that short trip, because you'd rather have your truck break down in Oakland than in the middle of nowhere where there's no service stations around. And so this means that we have regulations to limit emissions from trucks, but the dirtiest, most polluting trucks are concentrated in these communities. And so yes, we do want to live further away from that, but we can also address this by looking at the types of trucks and the standards that are being used in these areas and raising our standards regarding that.
And that's a really great point, Alexis. You hit on my other research topic. So one of the really cool things about California, though, is that we've had some really aggressive regulations in the last 10 years or so to clean up those truck fleets. And so the drayage fleet now, in especially the West Oakland area and around the state, are much newer. So they all have turned over so that they're now all 2007 and newer engines, which is phenomenally new for trucks, because like Alexis said, those trucks tended to be like 30 to 40 years old as opposed to just 10 to 15 years old. But one of the things that we've noticed is that now a majority of the pollution from those truck fleets is coming from a very small minority of trucks. So just a few trucks that maybe something's wrong, there's some maintenance issues or something's malfunctioning and leading to really elevated pollution levels. They're responsible for most of the pollution by the fleet. So if we can target those highest emitting trucks and fix them and repair them, you could continue to get these emissions reductions that then really protect community members. So that's a really great point, Alexis.
A great team, you two. There are several questions which all revolve around policy, and that's exactly what you were just speaking of too. We're curious, a few people have asked questions about, well, one, does this research specifically, is it going to go to inform policy directly, the research that you're doing with these sensors? And the other question around policy is, are there actual legal policies in place to protect people who are more influenced in the way that you're showing here, either in schools or in work? Are there any health exceptions or extra help to provide people affected by air pollution in these blocks and in these regions? That's a lot, I know, but.
Well, I'll tackle the first half of that just because I had some immediate thoughts. One of the really cool things about this area of research is it's very new. And so it's one of those things where you can't really make policy until you have data to understand what you're dealing with. And that's what this research has been able to show is here's some data. Now what can we learn and make change from it? I would say that because of the Assembly Bill 617 monitoring efforts, there's a lot more of this type of work happening, especially in environmental justice communities. And part of that work is to mitigate those pollution sources and mitigate that exposure. So there's definitely activity in that realm in terms of having this science to action and monitoring to advocacy work.
Yeah, and I can speak to the second point a little bit. There are regulations that protect the public from certain levels of air pollution. The kind of tricky thing about those regulations is that most of them have to do with outdoor air pollution, and that's really what we talked about a lot today. But indoor air pollution, especially if you're in a private residence, is really not considered the purview of the government. So when it comes to worrying about how outdoor air pollution might trickle into, get trapped in, and then be exacerbated by what's going on indoors, there isn't really a lot of protection with regards to that. But at the outdoor level, there are certainly fines for districts and industries that are over emitting. Those are assessed all the time. Something we might look into as voters and as a society is whether those fines are high enough and whether it actually disincentivizes the emission behavior, or whether it's kind of seen as a fee that you pay to keep doing what you were doing anyway. But those do exist, and if you're concerned about your area, you can file complaints related to that to try to get some action going. Which data is considered usable in those types of complaints is a little restrictive. So the EPA does have sort of licensing processes that say which types of instruments and techniques are allowed to be used to generate data that can then be used to assess these types of fines. But even unapproved measurement techniques can be used to kind of put political pressure on these types of systems. So even if you don't have, you know, a super high quality, super expensive monitor, even if you just have a purple air, that's still considered really persuasive at kind of the town hall level, and it is still something you can definitely bring to the attention of your representatives.
It's also something that it can highlight some of the personal activities that you might do in your own home that lead to higher exposure. So for instance, if you have your purple air kind of near your kitchen, whenever you're cooking, you're probably going to see a really large spike in PM. And so if that's an indicator to you that you're concerned about it, then potentially you could try to, you know, use the back burners and make sure that you have your ventilation hood on to push that that pollution up and out of your house, as opposed to right in your face as you're cooking. So things like that, you know, you can learn by having these types of sensors and having your own kind of experiments at home.
Thanks, Chelsea and Alexis, for those thoughtful answers. We've got a question about the low-cost sensors that you've both developed. So the question is, has the private sector made any progress in developing a cheap monitor for diesel soot? Or do you need more students to put together monitors for you in the future?
So on the BC side, that's definitely a tricky pollutant to study. The two students that worked on this project and actually developed this monitor have created their own business and are now selling them commercially. They're, of course, because now they're a business, not quite as low cost as the $500 per unit cost that we built them for in our lab, but I think that they're still pretty low cost compared to the other available instruments, but maybe not for something to buy in your own home. So that's on the order of a couple of $1,000 as opposed to a couple of hundred like the Purple Air monitors. But there's other commercially available kind of nodes that are actually the ones that are typically being deployed in these AB 617 monitoring efforts. So things like air qual and clarity nodes that include multiple pollutant species. And that's how they're able to kind of understand many sources or many types of air pollution all at once in one low cost node.
Right, before I ask my next question, I do want to say that all of this is being recorded and we will share it with everyone after the program. So then you can go ahead and share it with your friends and folks who missed. We've had a few questions coming through about whether or not this will be recorded, which is so exciting to hear. All of you want a little bit more, so that's great. The next question is an easy one. Maybe we can, if it's an easy one, and then we can just move on to the next one. But do you need internet access to host a sensor?
No.
No. Okay. There we
go. So for the sensors that we built, they stored the data locally, and then they also were transmitting over the 2G cellular network, which I don't think exists anymore. So when we redeploy these, we're gonna have to, re-engineer that side of it if we want to have kind of a live data stream. But we can always rely on the local data storage on just your standard SD card. And so that's where, to host one of our sensors, you just had to have a location that we could access about once a week for routine maintenance. And that was it.
What about Beacon, Alexis?
Ooh, So Beacon has a slightly different mission and angle in that it's a little bit sparser, but aimed at being a longer term type of installation. So Beacon has been operating in various forms since 2013, which is really exciting. But that means that we're kind of hoping to have a less frequent visitation of all of those sensors, because to maintain weekly visits to every sensor for 7 years would be too much. So yeah, the Beacon siting requirements are a little bit higher. For example, we can't power the Beacon sensors off of a solar panel, so we actually need a plug like you would have. Not a lot of folks have an outlet on their roof, so that's one of our big limitations. We are able to do some amount of the 2G cellular thing, but like Chelsea said, it's been really dropping off. So we usually, we connect to the Wi-Fi network of wherever the sensor is stationed. And that's a little more important for the Beacon network because we don't want to have to always visit that site to collect the data. Most of our sensors are actually stationed on top of schools. Schools tend to have outlets on the roof and some kind of Wi-Fi network, so it works out. And schools tend to be roughly spaced throughout a community at the kind of spatial resolution that Beacon is interested in. So we don't partner with as many private homeowners for the Beacon network just because we have that slightly higher level of requirements.
Alexis, do you do any like educational outreach at those schools? Is it like an educational opportunity for the school itself as well?
Great question, Chelsea. I feel like that was just a deliberate plug and I appreciate it. Yeah, absolutely. So Beacon was started with an educational component built in from the very beginning. I think one of our very initial partners way back when was Chabot Space and Science Center, which many of our audience members will be familiar with. One of our current partners is the Exploratorium Museum in San Francisco. And so in the Exploratorium, when it is open, you can see live displays of the sensors that are on the roof and interact with those displays. You can make your own graphs. But yes, at the classroom level, a lot of the Beacon team does these outreach visits, teaching the students in the classroom about what's going on their roof. And while it's not as appropriate for the elementary school level, at the high school level, students can download the data and a lot of them use the data in their science fair projects. They get some initial experience with data analysis that way. So yeah, it's been a really fruitful collaboration.
Awesome.
All right, thanks. Oh, thanks so much for those answers. So we've got another question for you. Considering the Bay Area has several functioning refineries, has there been any effort to understand their effects on neighborhoods in proximity to or downstream from the refineries?
So I'm not an expert in this, but I do know that there are some fence line monitoring efforts along those refineries, which I believe that the refineries themselves run as a response to some community concerns. I know one of the things that the Richmond community is very concerned about in terms of their AB 617 efforts is the effect of the Chevron refinery right there. So the sensors that we typically deploy probably won't be the best at capturing that impact because the refinery isn't known for, say, soot emissions. But for other organic species like volatile organic compounds, those could be significant and typically require more of these expensive, research grade analyzers as opposed to a low cost option. There's some low cost options, but they're maybe not as broad spectrum as that you would want to really understand that potential issue. So I think that's something that's in the works, especially for Richmond, but I don't know so much about what has already been done.
Yes, Beacon has a handful of sensors up in the Richmond area, and I know that there's been some mobile monitoring done as sort of an intensive campaign in that area. What I'll note in terms of kind of the future scientific challenges is folks who do air quality modeling, so try to make predictions based on what we already know about emissions, really struggle with the Richmond area. And the reason for that is that when we receive regulatory reports from emitting facilities about what they believe their emissions are, one company just has to report one number. So we get a Richmond Chevron facility number, but where is that coming from? It's not all from one giant chimney sitting on top of the Chevron headquarters, right? That would be astounding. It's actually distributed across like a very large area, thankfully. That probably helps mitigate some of the effects. But that spatial distribution is not part of the publicly available data set, and so it makes it very difficult to then predict what the downwind effects will be. And that's what we're excited to learn through future stationary and mobile monitoring campaigns.
Great responses. So are there any trends linking outdated appliances and utilities? So you're talking about the truck specifically, but what about other sources of pollution like appliances and utilities in residential areas that are linked also to poor air quality? And that kind of goes in with a second question. I'll pull these together. Are there any suggestions that these are linked to disproportionately to communities of color?
So that question's really out of my wheelhouse. But I know that there are many efforts up at Berkeley Lab, especially to understand appliances and the indoor space. So if you want more information from that, they have some websites, so you could go look at the indoor air group for Berkeley Lab. I think it just really depends on, again, the pollutant species that you're talking about and the way that you're trying to measure it. And so in terms of the networks that we're deploying, they're not going to be very good at picking up that type of an impact. And so the indoor space that Alexis was talking about and having indoor monitors would be much more effective for that question.
Yeah, I agree that indoor air quality is not really my expertise, but I think what Chelsea already mentioned about the stove, that's often the biggest source of indoor air pollution for most folks. It's especially an issue if you have a gas stove. Everybody likes gas stoves, but those are bigger PM producers than an electric stove. So if you have a gas stove, which in some cases is considered a more updated appliance, it really depends. You really want to make sure that you have some kind of ventilation, whether that's one of those hoods that appears over the stove. So that's kind of the sense in which the type of appliance you have could vary. But it's actually very interesting in terms of indoor air quality. It's not necessarily a straight correlation between that and the socioeconomic status or the racial makeup of the community. It's actually been seen in some cases that really new high-end buildings are so well sealed for energy efficiency that they seal the air pollution in. So in that sense, having kind of a drafty house might be helping you out. But I know what's been sort of anecdotally established in some environmental justice communities is to look at the windowsill. So do you see the soot building up on your windowsill when the window is open or when the window is closed? And that's your go-to indication of whether your significant sources are outside your home or whether they're coming from inside the house. So that's a real low-tech way to make sure that you're protecting yourself against the largest impact on your personal health.
Thanks, Alexis and Chelsea. We got one more question that just came in. Chelsea, I think this one might be for you. Did the diesel trains run by Amtrak in the West Oakland corridor have a significant contribution to air quality?
So in terms of their proportional impact or proportional contribution to overall emissions, I don't know the answer to that one specifically. That would be a question for the Air District's emission inventory, has that type of information. They definitely do spew black soot though, if you watch them go by. But I think that one of the things about trains is that they tend to be more infrequent and short duration within a community. And so in terms of that impact on the overall West Oakland community is probably small compared to that of trucks. However, if you're a house that is right next to a railroad, there it could be a pretty significant fraction of your overall exposure. So like we keep saying, it just depends.
Thanks, Chelsea. Well, believe it or not, I think we've reached the end of our questions. So at this point, I'd just love to say thanks so much to you and to Alexis for providing such engaging presentations on air quality in the East Bay and Bay Area. I also want to thank the audience for tuning in and asking really wonderful questions of our presenters today. We really appreciate you tuning in for this first session of the Midday Science Cafe. We hope you'll join us in the future for other presentations. Just as a reminder, if you want to stay in touch with us and learn more, you can visit Science at Cal at science@cal.berkeley.edu, and you can stay in touch with us at Berkeley Lab at lbl.gov. So from all of us, I just want to say thanks again, and hopefully we'll see you next time. Thanks, everybody.
Thank you.